All right, so let's finish off the topic of continuity. We've been talking about looking at a graph to determine continuity, and we've been looking at equations, and we've been evaluating continuity at a point. But there are sometimes we know that a function is not continuous everywhere. However, it might be continuous in some places. It might be continuous on an interval, or it might be continuous from just one side or the other, like from the left or from the right. So if something is right continuous or continuous from the right, that just means that the limit from that side is the same thing as the value at A. So if it's continuous from the left, you can see the limit from the left would be the same thing as f of A. So look at example 3. This is actually the graph of the greatest integer function. But if we take the limit as x approaches 2 from the right-hand side, okay, so here's 2 right here. So if we're approaching that from the right-hand side, we would be coming in on this piece of the graph right here. And so you can see that's approaching a y value of 2. Then if we're approaching 2 from the left-hand side, so again, here's 2, and approaching it from the left-hand side, we would be on this piece of the graph right here. So you can see that would be a y value of 1. So then f of 2, when you actually plug 2 into the function and see what y value you get, this is an open dot, this is a closed dot, so it's this value right here, it's 2. So since the limit from the right is the same thing as the function value, then we could say that this is continuous from the right, or right continuous. So again, that's this definition, that if the limit from the right is equal to f of A, then it will be continuous from the right. All right, let's look at another one. So looking at the graph of y is equal to the square root of x. All right, for y is equal to the square root of x, is it continuous everywhere? Well, no. You can see that I can only draw it without picking up my pencil on this right-hand side. It doesn't even exist over here on the left-hand side. So when we say on what interval is it continuous, where can we draw it without picking up our pencil? Well, we can start at 0 and we can go to infinity. And so it would be continuous on that interval from 0 to infinity. Then we want to look at, is it left or right continuous? Well, if you'll notice, as we're approaching this from the right-hand side, the limit from the right is the same thing as f of 0. And so it is right continuous because the limit from the right is the same thing as f of 0. We get 0 for both of those values. Now, something else that continuity can help us with is, because when we say something is continuous, that means that the function is defined, the limit exists, and f of A equals that limit. Then let's say that they tell us a function is continuous, so we know those things to be true. They give me this function and they say, find f of 2. All right, well, I may not know f of 2 because you can see when I plug 2 in here, I get 0 in the denominator, and that's undefined. So I may not be able to find f of 2, but I know that f of 2 is the same thing as the limit. So I may be able to find the limit. So let's try that. Let's try finding the limit as x approaches 2, because then that will tell me what f of 2 is. All right, so this is a rational function. So rational functions are continuous within their domain, meaning we can just use direct substitution as long as we don't get 0 in the denominator. Unfortunately, we get 0 in the denominator. Does that mean the limit doesn't exist? No, that just means that it's not well behaved. So I want to try to use some of those things we learned earlier in the chapter to simplify this and perhaps make it well behaved. So remember that we talked about you could factor and cancel. So when we factor and cancel, now what I have left is a polynomial, and when I'm taking the limit of a polynomial, I can just use direct substitution because it is well behaved. So since the limit is equal to 4, then I know that f of 2 is equal to 4. So these little 3 dots here, they mean therefore, so that would be our proof that f of 2 could be equal to 4. All right, so look at example 5. Here's another polynomial, limit as x approaches -2. So remember that rational functions are well behaved within their domain. So we always want to check them first and see, can I just do direct substitution? Don't assume that it's always going to be 0 in the denominator. So you'll notice for this one, I was able to just do direct substitution and get my limit. Now, we've learned previously that polynomial functions, rational functions, and root functions are well behaved within their domain. And in this section, we've learned that well behaved and continuous are the same thing. So you'll notice now they're telling us that polynomials, rational functions, and root functions are continuous for the values that are in their domain. Now remember that for the root function, we've talked about before that when you get the square root of 0, that the limit is only going to exist from one side or the other. So with a root function, it's going to be continuous from the left or continuous from the right, but not both. All right, then they also add in another piece here, and that is trig functions. All right, think about the sine curve. The sine curve has a domain of all real numbers, so it would be continuous for all real numbers. The tangent curve, however, has places where it's undefined and has vertical asymptotes, right? So it's not continuous at those values. You'd have to pick up your pencil when drawing that. So it makes sense then that trig functions are also going to be continuous at the values in their domain. All right, so let's look at a couple of things and talk about where they would be continuous. All right, so if we look at this first function, what kind of function is this? Well, it's a polynomial. So polynomials are continuous within their domain. What is the domain of that polynomial? All real numbers. So it's going to be continuous everywhere from -infinity to +infinity. All right, look at the next one. For the next one, we've got a rational function. Remember, we said rational functions are also continuous in their domain. So what we need to exclude from the domain is just where the denominator is equal to 0. So if you set x squared minus 1 equal to 0, you'll get +1 and -1. So it's going to be continuous everywhere except for +1 and -1. So we could say all real numbers except for 1 and -1. If we had to give interval notation for that, it's going to be -infinity to -1. And then we're going to have to pick up and jump over that problem at -1 and go to +1, and then pick up and jump over that problem at +1 and go to infinity. Now the next two that we have are a combination of functions and a composition of functions. So if you have a combination of functions, the combination can only be continuous where all of the parts are continuous. So what I need to do is go through and figure out continuity for each part and then see where all 3 pieces are continuous. That's the only place that h of x can be continuous. All right, so let's start with the root function. Root function is going to be continuous in its domain. So let's think about the domain. When you have a square root, you take what's under the square root and set it greater than or equal to 0. So our domain then is greater than or equal to 0, and there's our interval notation for that. All right, look at the next one. For the next one, we have a fraction. So again, rational functions are continuous within their domain. What's not in the domain is where the denominator equals 0. So we're going to say that x minus 1 can't be equal to 0. So that means that x cannot be equal to 1. All right, and then this last piece, again, rational function, denominator can't equal 0. But if you set x squared plus 1 equal to 0, you move the 1 to the other side, you'll have x squared is equal to negative 1. Take the square root of both sides and you get imaginaries. So the only thing that we would have to exclude is imaginary values. So that means that its domain is all real numbers. We would only need to exclude imaginaries. Okay, so now I need to put all three of these pieces together because, again, h of x is only continuous where all three of these are continuous. So basically, I need to state from 0 to infinity excluding 1. So interval notation for that, 0 to infinity excluding the 1, you can see we're going to go from 0 to 1, pick up and jump over where that problem is, and then go on from 1 to infinity. All right, look at the composition of functions. A composition of functions is when we have the one function inside of the other. We've worked with these already this year. So you can see that if g of x is x squared, if I put x squared right here for g of x, I would have f of x squared. That means put x squared in the f function. So if I put x squared in for x, that would be sine x squared. So you can see how we're getting that composition from these two functions. All right, when you're looking for continuity for the composition, you need to look at the two pieces that are making up that composition and see where they're continuous. So for g of x, it's a polynomial, so it's going to be continuous everywhere. And for the sine of x, trig functions are continuous in their domain, and the domain of sine x is all real numbers. So all real numbers overlapped with all real numbers is going to give us all real numbers. All right, the last thing we want to talk about is the intermediate value theorem. The intermediate value theorem starts off by saying, let f be continuous. All right, so number one, we're going to have to start with checking continuity. All right. Then it says, let f be continuous over a closed bounded interval from a to b. So we're looking at an interval that starts at a and goes to b, right? It says, if z is any real number between f of a and f of b, then there is a number c in that interval so that f of c is equal to z. All right, so here's what they're saying. If there is a y value in between f of a and f of b, then there has got to be an x value that goes with it in between a and b, because you can't have a y value without having an x value. So we're going to apply the intermediate value theorem in several different ways this year. But this first application that they give us is they want us to tell, is there a root between f of 1 and f of 2 using the intermediate value theorem? How do we do that? Well, we could graph it. We could go through and graph this whole cubic right here. And we would be looking, of course, for an x-intercept because that's the same thing as a root. But there's an easier way to do that with the intermediate value theorem. Now remember, the theorem starts off with saying a function has to be continuous. So, okay, we've got a polynomial. It's continuous, so I can check off continuity. That's good. And we're also interested in the x values and the y values, right? Because that's what the theorem said. So let's go through and let's take 1 and plug it into the function, and take 2 and plug it into the function, all right? So if we plug in 1 and 2 into that function, we're going to end up with -1 and positive 12. So basically, you've got the point 1, -1, and you've got the point 2, positive 12. If we went from negative to positive, we had to cross through 0. Or if we went from positive to negative, we had to cross through 0. So the second thing that we want to look for is we want to look for a sign change. So if this is a continuous function and if it has a sign change, then yes, I can say that there is a root between those two values. All right, here's how the intermediate value theorem comes into that. Since our function is continuous, because all polynomials are continuous everywhere, and n is equal to 0 is a number between f of 1 and f of 2. Okay, so 0 has got to be in between -1 and +12. Because there was a sign change, I know there's a 0 in between those values. Then by the intermediate value theorem, if I have a y value in between these two y values, there has to be an x value in between these two x's that goes with it. So there has to be an x value that's between 1 and 2 that would go with that y value of 0. And therefore we know that there's at least one root between 1 and 2. So that's how the intermediate value theorem could be applied in that situation.